Propositional logic not only introduces basic principles of mathematics, but also computer science and many other disciplines, like philosophy, for example, because it helps us to correctly reason. It helps us to accurately and formally describe the outcome of a method and to write correct software, for example. If you write a conditional statement, you use logic. Propositional logic is also at the core of computer hardware. You have or you will encounter propositional logic again in the course System Architecture. We have to introduce some terminology first. We will learn what are propositions, logic connectors, truth tables, tautologies and contradictions, and finally logical equivalence and implication. Propositional logic is based on representing the world in form of statements that have a truth value, which means they are either true or false. Such a statement is called a proposition. For example, the statement Al Horford is tall is a proposition. Considering that Al Horford is 6'10", this is a true statement. The statement Kyla Ross is tall is a proposition as well. Kyla Ross is only 5'3", so I think we can agree that this statement is false. Nevertheless, it is a proposition. A question like, is Tom Cruise tall, is not a proposition, since it's not a statement. Similarly, the exclamation, Go Wolves, is not a proposition. This statement does not have a truth value. A proposition can be more complex. For example, the following sentence is a compound proposition. CS1302 is a prerequisite for CS3151, and CS3151 is a prerequisite for CS3152. Propositions are typically represented by lowercase letters. I will call this letter often a logic variable. A logic variable is used in many respects similarly to variables used in algebra, but a logic variable can only have the value true or false. It cannot have a numeric value, for example. A proposition that cannot be split into smaller propositions is called a prime proposition or atomic proposition. The statement Al Horford is tall is a prime proposition. So is the statement Kyla Ross is tall. However, the statement CS1302 is a prerequisite for CS3151 and CS3151 is a prerequisite for CS3152 can be split into the two separate propositions CS3002 is a prerequisite for CS3151 and the proposition CS3151 is a prerequisite for CS3152. You are already very familiar with propositions as you all have written Boolean expressions as conditional statements in an if statement or as a loop condition. A Boolean expression is the same as a proposition. A Boolean expression is named after George Boole, who introduced a way to manipulate logic expressions. The term Boolean logic is also another expression for propositional logic. So here's a Boolean expression used in a conditional statement. Not Q is empty and not stack is full. This is a compound proposition as it connects two propositions by the AND operator. The proposition uses also the negation operator. You are also familiar with the OR operator in Java. There are several other operators that connect propositions. We'll have a closer look at the operators we will be using. The negation operation uses the NOT operator. The symbol looks like a dash with a little tail. The conjunction is an operation that uses the AND operator. The AND operation symbol looks like a flip V. The disjunction operation uses the OR operator, which looks like a V. The implication operation uses an arrow pointing to the right. Finally, the equivalence operation uses a two-sided arrow. The compound proposition we have seen before, CS1302, is a prerequisite for CS3151, and CS3151 is a prerequisite for CS3152, uses a conjunction, that is, the logic AND operation. If we represent the first part of the compound proposition by the logic variable p and the second part by the logic variable q, then we can also rewrite the compound proposition as p and q. You know the negation, the conjunction and the disjunction operations from Boolean expressions in Java. Just the used symbols differ, but the meaning of the operations is the same. Note that there is no implication operation and no equivalence operation available for conditional expressions in Java. So what is the meaning of all these operations? If we connect propositions by logic operators, the result is again a proposition that has a truth value. The resulting truth value depends on the value of the operand and the operation. We can describe the outcome of an operation through the use of a table. We use one column for each operand, and one column, the last one in the table, shows the resulting truth value of the operation. The negation operation is applied to a single operand only, and thus there's only one column for the single operand and one column for the result. Each row corresponds to a possible truth assignment to the operands. The negation operation flips the truth value of the operand. Thus, if p has a value true, then not p is false. If p is true, then not p is false. We use the capital letter T and F to represent the truth value true and false respectively. The conjunction connects two operands, say p and q. The result of the operation is true if and only if both operands are true. So if both operands are true, then p and q is true. In all other cases, p and q is false. Note that the table has 4 rows showing the possible truth assignments to the two variables. In case of the disjunction, the operation p or q is true if at least one of the operands is true. Thus the operation has the value false only if both operands are false. The conjunction is called the inclusive OR. You might know about the exclusive OR operation. This operation differs from the conjunction. In the case of the exclusive OR, p or q is true if exactly one operand is true. We will not use the exclusive OR operation here. The implication operation, p implies q, is true if p and q are both true or if p is false. If p is false, then q can be true or false. In either case, the implication is true. Basically, the implication requires that q must be true if p is true. If p is false, then there's no requirement imposed on q, and q may be true or false. If this confuses you, just accept it as a definition of the implication operation for now. The equivalence operation, p is equivalent to q, is true if and only if both p and q have the same truth value. So if both p and q are true, or if both are false, the outcome of the operation is true. Now we can form more complex expressions like p or q and r. The truth value of the operation depends on the values of p, q, and r. Let's say p and q are true and r is false. As q and r is set in parentheses, we evaluate the expression, and it is false. Then we evaluate p or q and r. P is true and q and r is false, thus the entire expression is true. What happens if we change the parentheses so that p or q are in parentheses? Then p or q is true, but the expression true and r is false since r is false. So generally, the order in which a more complex proposition is evaluated does matter. Now let's drop the parentheses at all. How is this expression evaluated? Well, there's a precedence defined on the logic operators. For example, the conjunction has precedence over the disjunction. Therefore, we have to evaluate the conjunction first and then the disjunction. So the expression has the same value as the very first expression, where q and r are set in parentheses. The negation operation has highest precedence among the logic operands. Then comes the conjunction, disjunction, the implication, and the equivalence operator has lowest precedence. A truth table lists all the truth values of a proposition it has for the different assignments of truth values to its underlying logic variables. Consider, for example, the proposition P or not Q, in parentheses, implies R and P. There are three logic variables that occur in the proposition, P, Q, and R. We need a column for each of the logic variables. Each row corresponds to a truth assignment to the three variables. There are 8 different truth assignments. For example, one truth assignment is where all 3 logic variables are true. Another truth assignment is where P and Q are true but R is false, and so on. The last column is associated with the actual proposition and contains its value under the corresponding truth assignment to P, Q, and R. If the proposition is rather complex, it is very helpful to evaluate first some parts of the proposition rather than trying to evaluate the whole statement in one step. We can add some columns. For example, we can add a column for the part P or not Q and one column for the part R and P. Let's look at the truth table of the proposition P or not P. You can see that it evaluates to true, no matter what truth value the variable P has. Such a proposition is called a tautology. There are terms for other special kind of propositions. So again, a proposition that evaluates to true under every possible truth assignment to its logic variables is called a tautology. In other words, a tautology is a statement that is always true. If a proposition evaluates to false under every assignment to its logic variables, it's called a contradiction. If a proposition is not a tautology and not a contradiction either, then it's called a contingent proposition. In other words, a contingent proposition is true under at least one truth assignment and false under at least one other truth assignment. The next 3 slides show example propositions. Halt the video, create a truth table, and try to verify that each proposition is a tautology, contradiction, respectively a contingent proposition. Here are some tautologies. These 3 are contradictions. Most propositions one encounters are contingent propositions. Here are 3 examples. The last 2 terms I'm about to introduce, that is logical equivalence and logical implication, are important to reasoning. 2 propositions are logically equivalent basically if they have the same meaning. Formally, 2 propositions P and Q are equivalent if and only if the proposition P is equivalent to Q is a tautology. Thus 2 logically equivalent propositions always evaluate to the same truth value. Their truth table is the same. Observe the different symbol for the implication operation and for the logical equivalence. A proposition P logically implies a proposition Q if P implies Q is a tautology. In other words, whenever P is true, then Q is also true. However, in contrast to equivalence, it is possible that P is false and Q is true. Again, observe the different symbol for the equivalence operation and the logical equivalence.